on Zoom also.
Yeah.
Yeah. Nice. So should we? I'm good. Should we start?
Yeah.
I'm just discussing with. Okay, so welcome to the morning session of today of the conference GSI. So the session will be chaired by myself and Cyrus. Cyrus is virtual, and so the session is on the probability and statistics on Riemannian manifolds. And the first presentation will be given by Salem Said. And it's entitled From Bayesian Inference to MCMC and Convez Optimisation on Hadamard Manifolds. Salem. Thank you very much, Xavier, and thanks to everyone for being here. My talk, well, the aim of my talk is to run the machinery of Bayesian inference on a particular problem where the data belongs to a certain kind of Riemannian manifold. As you all know, Bayesian inference requires certain specific tools, such as MCMC sampling and also optimization. And therefore, I will be developing these tools as required for Bayesian inference on a Riemannian manifold. So the class of Riemannian manifolds I will be studying is
maybe we'll interrupt just one second
problem.
Because this is not broadcasted on Zoom.
Oh, screen sharing, yes.
It is shared. Yes.
Nice.
Thank you.
Oh, so to go on, the class of Riemannian manifolds I will be considering, first of all, is the class of non-compact symmetric spaces. Of course, these include Euclidean space as a special case, and they're mostly interesting to us because they contain all the different kinds of cones of covariance matrices, real, complex, quaternion, etc., as well as block toplets, block, all these kinds of covariance matrices. And geometrically, any one of these manifolds is a totally geodesic subspace of the cone of real covariance matrices of higher dimension. These spaces are interesting because they have connections to random matrix theory, and also because they're related to advanced questions of matrix factorization. So for general background, I put these two references for you, which you may want to look up, and they basically show the cross-subject connections of the Riemannian geometry of non-compact symmetric spaces. But this isn't my topic today. My topic is Bayesian inference, right? I'm going to look at a certain kind of probability distribution called the Gaussian distribution defined on a non-compact symmetric space. And it's given basically by its probability density, which has a usual Gaussian dependence on squared Riemannian distance rather than Euclidean distance. So these have simple properties which lead to the fact that maximum likelihood inference has a simple and very interesting property. If you look at the likelihood function where the data are called yn, you will see that it separates into a part that depends on the barycenter parameter x, the centroid parameter, and another one on the dispersion parameter sigma. And therefore, maximum likelihood is equivalent to a least squares problem to computing a Riemannian barycenter. And this is kind of the defining property of Gaussian distributions. Moreover, they also satisfy a maximum entropy property. These distributions maximize Shannon entropy for a given centroid, i.e. barycenter and dispersion. So let's look at Bayesian inference. We want to apply Bayesian inference for the parameter x, the centroid parameter. My observation is called y and my parameter is called x. And of course, the first thing to do is to choose a prior. And not surprisingly, I will choose a prior that is also Gaussian. So my posterior density is the product up to a normalizing factor of the prior and the likelihood. And since they are both Gaussian, the posterior density looks like this. It's exponential of a combination of squared distances. Well, for a single Gaussian distribution, as in here, we know how to compute the normalizing factor Z. However, in this case, the normalizing factor will remain missing due to lack of symmetry. So we have to accept that we're working with a partially unknown distribution. So I'm going to look at two kinds of Bayes estimators, the maximum-a-posteriori, which is the mode of the posterior distribution, and the minimum mean squares, which is the Riemannian barycenter of the posterior distribution. The maximum-a-posteriori is a geodesic convex combination of the prior centroid Z and of the observation Y. This is typical Bayesian thinking, where we have a convex combination of the prior and the observation, and the weights, of course, depend on their respective variances. This is easy to compute, but the MMS involves minimizing a function. How do we compute the MMS? It's the solution of this minimum mean squares problem, which is a strongly convex problem. It has a unique solution. We want to minimize E of pi, but we don't know how to compute this integral. Therefore, we need to come up with a computational strategy. It consists in one using Markov Chain Monte Carlo to sample from the posterior density pi here. And then we solve a convex optimization problem which approximates this problem. Of course, an alternative approach would be to use the samples in the framework of an online optimization method, such as stochastic gradient descent. At the end, I will, Riemannian stochastic gradient descent. At the end, I will explain why I prefer convex optimization in this context to Riemannian stochastic gradient. In any case, there are certain cases, special cases, where the map and the MMS are equal. Of course, in Euclidean space, they are always equal. In general, for any Riemannian symmetric space of non-compact type, if rho, so rho is this coefficient here, it's the tau squared. This is tau is the prior variance over sigma squared plus tau squared, right? This is the important parameter in the usual Kalman filter formula, let's say, in classical Gaussian Bayesian inference. If rho equals to 0 or 1/2 or 1, we know that the map and the MMS are equal. This is a proposition. So on any non-compact symmetric space, rho equals 1/2, well, or 0 or 1 implies that MMS equals to map. And this is interesting because the map can be computed directly without need for sampling. In general, we want to investigate the relationship between these two, and therefore we need to apply our computational strategy. We want to look at the Metropolis-Hastings algorithm in order to sample from the posterior density, and therefore approximate our cost function, our Bayesian cost function, I should say. So the Metropolis-Hastings algorithm, you all know it very well. Basically, you have a proposed transition density, you make new proposals. And if these proposals increase the posterior distribution, you accept them. If not, you accept or reject them with a probability called alpha here, which is the minimum of 1 and the likelihood ratio. So you accept good propositions and maybe you accept bad propositions for the sake of moving around. And what we want to guarantee is geometric ergodicity. This means the distribution pi n of the sample xn converges exponentially fast in the TV norm to our target distribution pi, the posterior. And geometric ergodicity guarantees that a strong law of large number is satisfied. So we have this property where empirical means approximate expectations with respect to the posterior. So in our case, we have a big theorem, which is proved in the paper, I guess, that I'm presenting. that says that under certain conditions, xn generated by the MH algorithm is geometrically ergodic. Under certain conditions, which we can discuss in the questions if you want. In our case, in the case of the posterior distribution here, which you can see here, all of these conditions are satisfied, meaning I can apply Metropolis-Hastings to sample from the posterior distribution, and I have this empirical cost function here, En, and it converges uniformly on compact sets to the Bayesian cost function, E pi. And moreover, we have that the minimum x hat n of En converges with probability 1 to the MMS Bayesian estimator. So we're going to use x hat n to approximate x hat MMS, and x hat n is the solution of a strongly convex optimization problem because the function En of W is strongly convex. So we're going to apply gradient descent, as you can see here, Riemannian gradient descent with a constant step size to the function En, the empirical Bayesian cost function. So if I have a function defined on a Hadamard manifold and it's C1 and it's strongly convex, and if my iterates, if my gradient descent iterates remain within a set where the function has is L smooth, it has L smooth gradients, means it has upper bound on its Hessian. If I choose any step size which is smaller than 1 over alpha and 1 over L, so alpha is the lower bound on the Hessian, L is the upper bound on the Hessian, then I obtain an exponential rate of convergence for my cost function. The rate is 1 minus mu alpha. The proof follows from the so-called PL inequality, which is easy to generalize from Euclidean space to Riemannian space. So using an exponential map, we have, using the Riemannian geodesic map here, exponential map, we have an exponentially fast rate of convergence. And in fact, in this case, it would be a bad idea to use a retraction instead of the exponential, because retractions don't guarantee such fast convergence rates. So even though the exponential is more costly, but it converges so fast that you'll do so much less calculations. It's going to converge in, let's say, 4 to 7 steps, whereas the retraction is going to converge maybe in 500 steps. So using the exponential is better. So now we have our computational strategy all done. Let's see what it tells us about the MMS estimator. So as a case study, I work on a hyperbolic space of dimension D, meaning it has constant negative curvature. So here you have the two-dimensional case. The square is the prior, the circle is the observation, the gray dots are the samples generated by the Metropolis-Hastings algorithm, and the black dot is the barycenter of the samples. And very surprisingly, the barycenter of the samples lies on the geodesic between the prior and the posterior, just like the map. And in fact, if we look at any dimension, and if we increase the dimension gradually, the distance between the MMS as we approximate it and the map doesn't grow with dimension at all, and it's very, very small. It seems that due to many computational experiments which we have carried out, it seems that X hat MMS and so the MMS Bayesian estimator and the map Bayesian estimator are very, very close to each other in any dimension. And so I have an open problem which I would like to answer and also to well, I guess present to you if you would be interested in thinking about it. Are they actually equal in certain cases? What's the distance between them like, generally speaking, in case they were not equal? But they're very close to each other anyway. So this is, I guess, I want to stop on this open problem, which is very interesting and which I would like to share with you. So thank you for your attention.
Well, thank you for the very nice presentation. So I will first ask if there are questions in the room, and then we'll Cyrus can grab the questions from the Zoom session. So is there any question? So I've got a few of them.
Yeah.
So maybe the first one is on the equivalence between MMS and MAP.
Yeah.
So right now your results are in negative curvature and for isotropic Gaussian.
Yeah.
So what is your feeling about going to positive curvature and to non-isotropic Gaussian?
I haven't done any experiments in positive curvature. I think, so I don't know, in fact. Going to non-isotropic Gaussians, I think the same kind of result may hold. Again, I'm not sure. I haven't done sufficient experiments about that. I guess the advantage of the map is that it can be computed without sampling. It's so much easier to compute. So would it be a good first approximation, at least to the MMS, is the general question. Because
actually the second question on that line is what you have right now is two isotropic Gaussians. Mm-hmm. So if you actually look at there is still a circular symmetry mm-hmm. of all your densities around the geodesic. So if you take any point of the geodesic, the distribution should still be circular symmetric, which is why the both have to be on the, I guess, on the geodesic. Yeah. And so this intuition would say this should go to positive curvature, but not to non-isotropic. I absolutely agree with you. So I'm looking for the reason why they are so close to each other, or maybe why they are equal. And the reason why it seems that this is because there's some new symmetry, as you mentioned, rotation mm-hmm. about the geodesic, that forces the MMS to be on the geodesic. And then simply by continuity, because it's equal to the map when rho equals 1/2 or 0 or 1, basically by continuity, it has to be equal to it all the time, because just by taking a derivative. So the big question, I agree with you, would be to identify this hidden symmetry, which is related to having circular isotropic Gaussians. It wouldn't hold otherwise. But what is this hidden symmetry? I'm not sure. Yeah, so I haven't formulated it yet. Yeah. Good. Any other question in the room? Yes.
Thank you, Salem, for the presentation.
Thank you.
Did you experiment on other spaces that don't have a constant curvature?
Yeah.
And was the gradient distance stable enough that you could keep the constant step? Because sometimes to estimate means it's useful to decrease the step.
Yeah, so I was using a step size equal to 1. And as the dimension increased, even 20, dimension 20, dimension greater than 20, the convergence always held in, as I said, 4 to 7 iterations. So the thing is, you want to take mu as big as possible within this constraint, and you'll get something good. I have done experiments on spaces of covariance matrices, so not constant curvature. I still get this very, very good convergence. But for now, it doesn't seem to me the distance is so small here. Yeah. So maybe the result is really in constant curvature.
Okay, so let's thank the speaker again. Let's go to the second talk. So Simon.
Who is online?
Is
Stefan Huckman and Veteran.
Oh, so that's not the order of the program. So which order are we following right now? I'm a bit lost.
That's not the order? Okay.
Simon Evelyn, are you?
No, c'est
c'est la vidéo. Okay, that's the video.
Yeah.
That's the podcast now.